So is the screen is visible?
Yes, sir.
Okay, okay. I think 2 students have not joined. Okay, let's start. So in the previous class, we have discussed about, let me just, so in the previous class, what we have done, we have studied about the basics of measurements and the types and sources of errors. And gradually we realized that, yeah, any doubt? Okay, so I mean, in the previous class, our objective was to, uh, get a little understanding about what are the measurements, what are the errors, the sources and types of errors. And we have realized this fact that, okay, we are not very much interested in outliers and systematic errors as part of discussion, but in random errors we have to discuss a lot more things. And the reason was simple, that uh, obviously because of the nature of the random error, that it is out of control, they are bound to happen and they will happen. And while you use those measurements for any kind of system development, model development, or any kind of data processing, then you need to realize that if you do not do something to those errors, they will eventually propagate to in a larger manner, and it will lead to certain incorrect assessment or incorrect estimation of something. This was the idea. And in that process, we realized that, okay, if we have to deal with the random errors, now it is very important that you must understand that when we have to deal with random errors, we have to understand a little more about the probability distributions, because the random errors, they are not deterministic in nature. You cannot find a single value, isn't it? Instead, they have a frequency of occurrence. Okay? As if that error which is there in the measurement, it will have 3 components, may have 3 components, otherwise it may have only 1 component. The chances of outliers is less if you are very careful, and if you know how to understand those errors which may fall in the category of outliers. So obviously outliers chances are very less considering the sophisticated instruments that are available right now. But chances of systematic errors are always there. Random errors, you cannot control it, they are bound to happen. Obviously, for systematic errors, they are deterministic in nature, and you have certain mathematical models to deal with it. But when it comes to random errors, you do not have any such mathematical model. Instead, you have to understand the probability distribution, or the so-called the stochastic properties of these errors. Then only you will later on realize that you can estimate it, you can minimize it, and you can reduce it to an extent that ultimately it will be helpful for those observations to be used further in system. Now, having said that, our objective is to discuss further. That means it is true that in order to understand those random errors, we need to understand the mathematical model, and we have taken one example. And in fact, we have built our understanding is that how a probability distribution curve or function look like. In fact, the present slide shows the bell-shaped curve, which is very popular, and the equation represent that the probability of a value X, what would be the way, how would you compute the probability subject to availability of the mean and the variance. Now, what is more important is looking at this basic understanding is that what is eventually we are dealing with. In order to understand that probability distribution function or any kind of function which you will use further, so one question you should immediately ask to yourself, why we are using those probability function, isn't it? Why not a mathematical function? The answer is very clear, because we have to deal with random errors and they do not follow any sort of mathematical model. So obviously you need to understand the probability function. The second is, what will be the benefits of using such probabilistic or probability distribution function? The answer is, you will come to know what is the frequency of occurrence and what is the probability of occurrence of a particular random error. Okay, so instead of estimating it in terms of its value, you are first estimating the probability of occurrence of a particular random error. Okay, so that is one most important thing to understand at this point, that instead of directly estimating a particular random error, because it is not a deterministic in nature, isn't it? We will only estimate the probability of occurrence of a particular random error. And in order to do so, we are using certain the so-called probability function. And later on, you will realize that with the same function which is written over here, you will try to solve as many as problems later on with the help of this function. And we will ask you to solve certain problems by estimating what is the probability of occurrence of this much error, what is the probability of occurrence of a random error to fall between these two values. So that's how we'll try to solve multiple problems subject to availability of a probability function. Starting will give you certain small functions, probability functions, and later on we'll solve major problem with the help of this bell-shaped curve, because directly starting with this bell-shaped curve might be difficult to some of you. Generally, people can, with the mathematical background, they can do it, but gradually will move from smaller or very easy kind of probability function, then gradually will move on to bigger functions. So this was the idea. But again, this has to be very much clear in your mind to all of you, those who are present, that we are using these probability function to estimate the probability of occurrence of a particular random error. Please remember, the reason why we are saying this statement, that probability of occurrence of a random error, because there is no single value of a particular random error. Okay. I hope the next slide is visible to you. Please let me know in case if it is not visible to any of you. Okay. The random variable. Okay. While working with the so-called random errors, we need to first understand what is the random variable. Please remember that at this point of time, we are simply understanding the random variable. There is no relation between random variable and random error as such right now. We just need to understand what is random variable, because it is a basic identity which is available to any introductory books. So our, in fact, measurements are variable, isn't it? Because whenever if I give you a task that go and find the measurement or the length of a table or any kind of length of an Earth observation, what you will get plenty much of observation, plenty much of measurements, and you will not have a single value. Instead, you will have bunch of values will have a same value. So you will have frequency of a certain number for a particular value. So with this understanding that there is no measurement is exact in nature, and you will have redundant observation, redundant measurements for a single quantity to be estimated, it means that your measurements are itself a variable. And that's why the term associated with observation will now be called a new, or will be known with a new terminology, which we call it as observables. Please remember, just before this class, measurements, observations, they were very simple to you, isn't it? But from here onwards, the observations are not error free. They are in fact with errors, and that's why they are variable in nature, and they will be known with a new terminology called observables. And in many of the geospatial adjustment computation books, just like I've circulated one, you will find this terminology quite often, that instead of writing observations, it will be written as observables. The same set, same bunch of information which you were given a task to collect from the field, like length of the table, length of area, width of the area, height of a particular angle of something, azimuth of something like this. So these are the individual observations which you have collected, but because of the nature that they are variable, we'll call them as observables. So similarly, in this slide, the random variable is introduced. The random variable could be anything. Your observations are random variable. Your error sources are also random variable. But obviously, we are more interested in random errors. That's why we'll discuss observables and corresponding random errors. Please remember, we are not discussing here right now, or not going to discuss more about systematic error. We are only discussing about the random errors. So just understanding with this concept, a random variable x is a rule or a function which associates a real number with each point in a sample space. And we can find this, understanding of this book even in your first chapter of your Mikhail and Gracie book, which I have just referred to. And in fact, you must have downloaded it from the MS Team and you have started reading it also. So just in chapter 1, this random variable concept is introduced. And in fact, it is written that it is your observations that are also variable in nature. In fact, the errors associated with them are also variable in nature. That's why both of them will be considered as a random variable. Okay. So, for example, just the classical problem of toss. The two identical coins are tossed. In the sample space, you will have HH, HT, TH, and TT. It's very, the result outcome would be in the sample space, you would have 4 such possibilities. And out of these 4 such possibilities, you can design any random variable. You can design any random variable as X that would take a value, isn't it? Yeah, this is a good time to introduce here that your random variable would be capital X, and that would be denoted by a small x, that would be a value. Okay, so your random variable X, capital X, which would take a value of small x, like the number of heads obtained, number of tails obtained, like that. Okay, so number of heads obtained, there would be possibility that there are a time, how many possibility in which heads would be obtained. So you will have so-called HH, HT, TH, and TT. Okay, so that is one chance that there would be such cases. Okay. Now, random variables may be discrete or continuous. The discrete random variable, obviously, the term discrete and continuous could be, realized from this fact that in your real world, there would be certain problems which may not have continuous in nature. It means they happen and something else happens after some time. Okay. So, considering those cases, your random variables are maybe classified in 2 types, maybe one in discrete, another is continuous. Now, in certain cases, you can also understand from this fact that discrete nature is something which I mean explains our limits to collect the observation. We do not have every time have luxury to have thousand or lakhs of observation. Instead, we have only hundreds. We'll start with only 100. Or maybe you could recall from your principle of remote sensing course that you will have a histogram. You have pixels, the DN values. That would be very limited, isn't it? You do not have much and large number of DN values. So for that, you will start with only histograms. And in fact, in the similar fashion, here also we'll start with discrete observables. We do not have luxury of going with the continuous observables. Okay. So the random variables that maybe of two types. One is discrete and that is continuous. And the discrete random variable assumes each of its possible values with a certain probability. Okay. So in the discrete nature, what will be there? You will have a probability for an individual random event, just like that. You will have number of events with the represented by small x, and then the corresponding probability that the x will take this value of small x. Okay. So in an experiment of tossing two coins, the sample space, as explained, that you will have HH, HT, TH, and TT, that will have 4 elements, and the probability of random variable x, the number of heads, assuming the possible outcome 0, 1, and 2. That means it will have no 0. Okay, it will have 1 possibility, and there will be a 2 possibility of heads. So probability would be explained by similar concept like that. Okay, and in the case of your continuous random variable, the probability of 0 of assuming any of its value, okay, and consequently its probability distribution cannot be given in tabular form. So in the case of the difference between discrete random variables and continuous random variable is very simple, that in the case of discrete random variable, you may have a tabulated information of the probability, which may be given by nothing but the frequency of occurrence of the event. Okay, and with the help of this frequency of occurrence of the event, you can form another column with the probability, and you must have done in your basic mathematics somewhere. But in the case of continuous random, you cannot make any such table, because how many times you will divide your space into multiple subset so that you could design your frequency of occurrence type of tabular information. So instead, you cannot form a particular table. Instead, you have to work with that function itself. Obviously, knowing that you have to, in order to find the probability of occurrence, you have to apply calculus, basic calculus, to reach a certain value. We'll discuss that part also. So the continuous random variable has a probability of 0 of assuming any of its values, and consequently its probability distribution cannot be given in tabular form. Or probabilities of continuous random variable are defined by specifying an interval within which the random variable lies, and it does not matter whether an endpoint is included in the interval or not. It's very simple definition, that instead of working with an individual value, okay, just like in the previous example, capital X is taking a single value of X or is equal to X. In the continuous random variable, you are working with an interval. That is the beauty of our real world scenario, that instead of working with an exact value in the discrete sense, in continuous, you are working with a range of values. That what is the probability that X would take from value from A to B, Y to Z, and so on. Okay, so we are more inclined towards continuous random variable. Obviously, we'll solve certain problem of discrete also, but obviously your understanding would be more towards continuous random. Why? Because in your basic understanding, you are not limited only with the 10 or 15 or 20 observation. Instead, our approach is to have more number of observation of a single quantity to be estimated. Okay. And in fact, the redundancy is the so-called backbone of any geospatial data processing. Whenever you work with remote sensing, whether you work with any GPS, radar, anything, you must have enough observation. And therefore, in many times, you would work with 10,000 set of data set at certain point. And the reason is simple, because the more you have data set, more you have choice to detect the errors, more you have choice to get a reliable estimate of something for an unknown quantity. So representation of random variable in the case of, obviously we are discussing the continuous case, so that the probability of probability of capital X lying between A and less than or equal to B would be denoted as probability of X within A and B plus probability of X is equal to B, which is obviously 0, which is defined that probability of an individual in continuous random variable would not be defined. So obviously we'll get the answer from probability of X lying between A and B. Probabilities of random variable X, which I mean, many times you will see a lot of formulas in your basic books that would be represented small x, small gx. So they all are represented by this fashion, that the subscript capital X represent the random event for which you are trying to measure or trying to form the distribution function, and that small x is the value which those random event is going to take. Similarly, the capital represent the cumulative distribution function and will be associated with any such PDFs. Now, please remember, whenever you trying to define a probability density function, you need to understand this point, that a probability model consists of one, random variable, and second, its density model. Okay, and it could be either your random variable and the probability density function, or your random variable and the probability distribution function. So both are used. Many times you do not have a density function, you have to work with distribution function, and later on you will realize that both are interconnected. You can work in any of them. So obviously this small f and capital F, they both represent, obviously the small f represent the density function, which we eventually write as a small, in a small letter we'll write as PDF, not the PDF which your document as a format extension, but PDF as probability density function. And the capital one is obviously represented with the capital letters CDF, or simply capital PDF, which is probability distribution function or cumulative distribution function. Okay. So eventually they are pairs. The function which is distribution functions, they are paired with the corresponding density function. Okay, so density function will have lower case letters, and the distribution function with the uppercase letters. So this is how they are represented. Please remember what we are trying to represent here. We are trying to represent a random variable with its density function. At the same time, we try to represent the same random event with its probability distribution function. Okay, we'll discuss the properties, but this is very important introductory statements that you should be careful of using. When you are using a small fx as a function, that would be nothing but the probability density function. And when you are using the capital fx, it is the okay. Some of you cannot hear me. One student is messaging as you are muted. Sumit, my voice is audible?
Sir, before 10 seconds, your voice was paused.
Okay, okay. Maybe because of some network issue, but eventually it should not be there.
Sir.
Okay. And the screen is visible?
Yes, sir.
Okay. So that was the representation of random variables. Coming back to again discussing the properties. So just carefully look in terms of the properties. Here in the first one, you will have density function, the small PDF. Sometimes those who have have little problem with understanding the probability concepts, they may find it little difficult, but otherwise it's very easy. It's very easy because you will have a lot of support in terms of solving any problem. Just try to carefully look at the representation manner, how we are representing these the density function and distribution function. So first is probability density function, which has properties, which is represented as fx is equal to, obviously when I say fx, it means I'm representing that capital X and small x together. Fx is equal to probability of x taking a value of small x. Okay, and cumulative density function, correspondingly capital Fx is equal to probability of x taking value less than or equal to x. That is the two major descriptive manner by which we can write these two different aspects. One is probability density function, another is distribution function. The notation in the first case, which is the summation, where k values from 1 to infinity, all such random variable, the summation of all would be 1, which is obviously meaning the probability of all random events, sum of probability of all random event would be ultimately 1. And in the second case, it is the fx, the capital Fx is nothing but the summation of all such probabilities that have occurred or that has possibility of occurrence. So what we are doing, we are adding the probabilities. That's why its name is cumulative. Eventually in your I don't know, somewhere in your 8th or 9th, maybe your 10th, you have used multiple tables, use multiple columns, and in one columns you try to add the cumulative manner, try to reach at the final values. Okay, so this is the properties of discrete RV. Please remember, in the discrete RV only you have used the summation sign. Okay, and obviously with your mathematical understanding, you can understand when you go from discrete to continuous, that summation would be represented by anyone. Can you guess? Any idea? It would be represented by integral. I hope it is very, quite straightforward to understand that your summation sign in your discrete manner would be ultimately represented by integral in the case of continuous RV. Is there any difficulty to understand this part?
No, sir.
It's very simple, isn't it? Okay, coming back to properties of continuous RV, as you could relate to, they would be curves instead of simple. And in fact, we have seen this, the nature of discrete as well as the continuous one in one of the figures. Let me just quickly go back to those figures so that would be better for your understanding. See, in this figure, you have reached from histograms or frequency distribution to a smoothened curve. And that's how the discrete as well as continuous nature can be explained. In your discrete nature, you will have probabilities at individual events, isn't it? And in your continuous random variable, you will have a smoothened curve. And that's why it is very easy to give probability of any random event taking a particular value in discrete, but it is very difficult to give any associated value for a similar random event in continuous random variable or a continuous distribution function. So for continuous random variable, the probability distribution function, which is fx and capital Fx, are curves which may take various forms depending on the nature of the random variable. Obviously, we will be more inclined towards later on to the bell-shaped curve, and we'll discuss the bell-shaped properties. But ultimately, what will happen that it may take any kind of nature of the curve. It may not be always bell-shaped curve. We are lucky that in our Geo-Informatics domain, majority of the distribution of observables are in the bell-shaped curve, but maybe in mechanical or electrical or maybe in some other domain, you may have seen some skewed distribution. They will not always be symmetric. So it is simply saying that it may take any shape. Okay. The probability density function, which we are using in practice to model the behavior of continuous random variable, and they are all always positive. That means they are above the axis, and total area under the curve bounded by the x-axis is equal to 1. Again, you just imagine the bell-shaped curve, and where you could see all the curve is above the x-axis. There is nothing part below the x-axis. That is what is written here. Okay. And the reason is simple. Why it is so? Because you are representing the frequency of events. Okay. You are not individually describing the event. Now on x, you have random errors, let's say, maybe. So x, that is a random error, will have equal chances of occurrence both in positive and negative direction. That's why x-axis has both two axes, positive and negative. And the representation, that means frequency of occurrence of such individual errors, would be represented by frequency of events, that is on the top side. Okay. And by such properties, you can go ahead and find the features of probability density function, which is nothing but fx will be always 0 or positive. That means event that will either not occur, or with 1 that will definitely occur. So the density function, which is represented at x from -infinity towards +infinity, that would be a integral from -infinity to infinity, fx dx would be 1. That means area under the curve would be 1. Please remember this very carefully, that area under the curve would be 1. The probability that a random variable x lies between any two values, maybe a and b, is the area under the curve between these two values. And that is nothing but integral of fx dx between a and b. Similarly, the cumulative distribution function would be represented by fx, that is probability x is taking values less than x, and is represented by -infinity to x. That means you are taking all values from -infinity to x. This is very similar. I mean, it's very easy to see in terms of mathematics because you are very familiar with calculus, but what is the physical significance? We are more inclined towards that. And in that manner, what we are trying to do, we are trying to find out all such probabilities all such probabilities of random event that has occurred before x, and we are adding all these. Now, I don't know whether many of you have the notebook or not, but it's very essential that you should write it at least once. It's very easy to watch these lectures online through your mobile, but what is ultimately, because if you were in a classroom and I would have been teaching, you must have been writing so many times these such equations, because that would ultimately give confidence that yes, we do not have any problem in terms of writing such equations. So at least try and write once how you represent the density function and how you represent the distribution function. Okay, I'm just giving you a time so that you could look at this slide, as well as at the same time you should write it at least once. These three boxes of equations which I've written, just try to see and observe. Any doubt? If there is no doubt, then you have to tell me what would be the value of f minus infinity. Again, I'm repeating, what would be the value of f, capital F minus infinity?
Sir, 0.
How?
So,
attempt करिए, थोड़ा कोशिश करिए, at least it would be discussed. First of all, you should clearly understand what is a small f and capital F. Small f is probability density function, capital F is distribution function, cumulative distribution function. And I am asking capital F minus infinity. That means cumulative distribution function value at minus infinity.
So the probability density function is from 0 to 1.
Probability density function is where no. Why,
Oh,
why
no,
it is
okay.
0?
No, sorry. The value start in a cumulative distribution function. The value start from minus infinity to plus infinity. So
No. You are mixing the two different things. Just make sure what you are saying. The answer is true. What I'm trying to say is the answer is true. Capital F minus infinity is 0 and capital F positive infinity is 1. But how?
Sir,
हाँ भाई,
because it's
दूसरा?
continuous random variable, so the value will be defined between minus infinity to x, between minus infinity and x,
Minus infinity and
x, between the range of minus infinity and x, and not the in मतलब criteria minus
good,
infinity and
good.
x.
No, that's true. That's true. That's the right answer, because in individual, when I say capital F minus infinity, what is generally, I'm trying to say here is because f of x, capital of f of x would be represented by probability that capital X is taking value less than or equal to minus infinity, and there is no such event below minus infinity. And in fact, capital Fx is represented as probability of x less than x. And in fact, in many of the slide, I was saying this. And in fact, in this slide only, you could see the last box, green box, where it is written capital Fx is nothing but probability x is taking value less than or equal to x. And where I'm replacing x with minus infinity, that means I'm trying to find the probability that random event takes value less than or equal to minus infinity. Okay, and if minus infinity is the extreme point, there is no such event below to minus infinity. That's why it is 0. But on the other hand, if I ask you what is the probability, what is the value of f positive infinity, that what you will say, probability of x less than or equal to positive infinity, and all such event has occurred. In fact, all total event has occurred. That's why it is, answer is 1. See, the reason why I've asked these two, because it is this is thumb rule, isn't it? The many times you will see in the book it is written simply f of minus infinity is 0, f of infinity is 1. But how do you realize it? That's very important. That will only be represented if you understood how the both PDF and capital PDF are represented. Okay. So correspondingly, if you see a bell-shaped curve lying between minus infinity to positive infinity, the corresponding distribution function or the capital PDF will start from 0, and it will be always increasing. It is non-decreasing function. It is always increasing. Any questions? It's very, very easy, although, but sometimes you some of you may find it difficult. So if you have any questions, it's good to ask here. Any questions that comes to your mind, but obviously subject to you have given little focus to what I'm trying to say here.
Sir?
Yes.
Sir, in PDF1, sir, if fx is always positive, then why are we integrating it from minus infinity to plus infinity?
That is again what I'm trying to say is don't confuse or mix two things. Small fx is integrated from minus infinity to plus infinity. Positive capital fx is not integrated.
No, sir, I'm saying so in front of the red one, which is written probability density function, the green box, in that fx bracket में fx is greater than 0 for every x, then integration from minus infinity to positive infinity fx dx is equals to 1.
हाँ, अब आप सोचिए क्या लिखा है, आप पहले रियलाइज करिए इसको, सिर्फ इक्वेशन पे मत जाइए, आप इसको फिगर से पहले रिप्रेजेंट करिए. पहले आप फर्स्ट वाले जो इक्वेशन लिखी है, fx x would always be positive and then subject to all x, पहले इसको आप बनाइए.
Understood, sir. Understood. Last time you have said that yes, sir. X can be in any direction, but the resulting comes in positive.
Yes, because it is ultimately the frequency of distribution.
Yes, got it.
Please remember, from my all the past 10 years of experience, these equations which are just written here, it may look little complex at some point of time because that's how our education has become. We are more on an applied direction rather than on the core mathematics or core science. So we may find it difficult, but believe me, it's very easy. It's just that you have to little bit more careful in terms of what you are seeing, what you are looking at. I hope it is clear to all of you. Let me ask you another question. Okay. The next question is, what is the capital F? When I say capital, obviously I wanted to make sure that you should follow that it could be cumulative distribution function. What is the capital F value at A? Be careful what I'm saying. Now you know all the basics. Everything is clear. Now my question is, what is the capital F value at A? How it would be represented and how would you approach it? अब जिनको difficulty हो रही है, what they can do, they can follow the last box, write the xk is equal to A. That's what I'm asking. F of A, capital F of A. So you'll just put the value of xk, small xk is equal to A. And on the right hand side will cite probability of capital X less than or equal to A. And then followed by integral of minus infinity to A. Any questions? That's how you will do, because I'll be giving the problems as an assignment today, and you will approach it with similar concept. Any questions? Should we go ahead? Okay. See that all we have imagined in the previous slide will be represented like this. See, it is cumulative distribution function. The word C represents cumulative distribution function for continuous orbit. It starts from 0, goes to 1. And the same question I've asked f of C, or just I've asked f of A, that is represented by nothing but the probability of x less than or equal to C. So probability that the random variable x takes value less than or equal to small x, x being a running variable which defines capital Fx or the cumulative distribution function. At probability density function such that the probability that a measurement falls between two values x1 and x2 is given by the shaded areas. Obviously, the moment you integrate it, integration is happens between that limit x1 and x2. अब आप लोग इसमें मुझे मैं क्वेरी करने जा रहा हूं, मैं आई वांटेड एवरीवन टू बी पार्ट ऑफ इट इन टर्म्स ऑफ आंसरिंग इट. नाउ टेल मी what would be the probability that x would take a value from A to less than or equal to B. Pehla, again I am repeating, what would be the probability of x that would take a value between A greater than A and less than or equal to B, and how it will be represented? बताइए राहुल.
Yes, sir.
बताइए. Probability with the same this concept of density function which is shown by the slide. What you have to tell me, the probability of random event x that is taking value between greater than A and less than or equal to B.
Just putting the value of A and B in x and x1 and x2.
Okay, that's fine.
And basically, in solving the integration, we can give it f as the upper value fb and minus and fa. Just solving the equation or putting the value.
Okay. But my next question is, how it is different from probability of x that is taking value between greater than A and less than B. In this case, less than or equal to is replaced by only less than. अब बताइए. If you look at this green box, I'm again repeating myself that what is the probability that event x would take a value from greater than A to less than B, and how it will be different from greater than A and less than or equal to B. Anyone who want to answer it? Bhagat.
Yes, sir.
बताइए. Two cases are given. One is less than or equal to. One is simply less than and greater than.
As far as I remember, all of them gave the same value.
All of them will give the same value. How?
How?
Okay.
In the few slide back, you gave the basic similarities between probability of x8. Okay. No, sir.
Again, the answer is true. Whether it is equal to or greater than or less than, or it is greater than or equal to, less than or equal to, whatever it is, answer would be same. But the question is how. Sumit, बताइए.
Sir, just now I'm not able to answer, sir.
Why? Are you not listening?
I was listening, but I'm not able to answer it, sir.
बहुत सिंपल, अभी बताया ना आपको, डेंसिटी फंक्शन की प्रॉपर्टीज बताई.
हाँ सर, पहले बताए थे कि ए से बी तक अगर इंटीग्रेट करेंगे तो उसको डिवाइड अलग करके लिखा जा सकता है ए से बी तक, प्लस और फिर एक्स जो जहाँ इक्वल होगा उसको फिर अलग से लिखेंगे, जैसे पी इक्वल टू
अलग से लिखेंगे और उसको फिर क्या कह देंगे कि वो वैल्यू,
उसको फिर वही इंटीग्रेट करेंगे माइनस इन्फिनिटी टू बी, जो जैसा जैसा रहेगा ऐसे.
और जो एडिशनल है जिसके लिए आपने इक्वल टू करके अलग लिखा है वो जीरो हो जाएगा, क्योंकि आपको कॉन्टिन्यूअस फंक्शन में इंडिविजुअल probability at individual point is not well. Okay, so it's very simple that in the case of greater than or equal to case, the equal to probability cannot be estimated. So obviously the answer would remain same for both cases, whether we are talking about the greater than or equal to or simply greater than. Okay, so coming back again to normal distribution curve. So obviously in Geo-Informatics literature as well as in many other areas, the normal distribution curve is frequently used probability density curve of a normal random variable, and which is represented by this 1 upon sigma root 2 pi. Obviously, don't get confused that sigma is written inside the square root. No, answer is 1 upon sigma root 2 pi exponential minus x minus mu square upon 2, or simply 1 minus 1 by 2 x minus mu by sigma whole square. So that's how you represent your distribution function. Now again my question is, what is this? It is a density function or it is a distribution function?
So density function.
Why?
Because f is in a small letter.
No. Hey, don't say like that. If it is in a small letter or simply look at the curve. Bell-shaped curve is always positive. Yes, bell-shaped curve is always positive, and all the x positive or negative respective, they will have a value in the positive side in terms of its ordinate. That's why it is density function. But the name and nomenclature is quite popular as normal distribution curve. That's why it is coming as. Okay. So yeah, correspondingly distribution curve can be made. Yes, that is another thing. Oh, I'm not declining the whole concept that you cannot make the distribution curve. You can make a distribution curve just by integrating from the so-called minus infinity to plus infinity, as you have done already. And similarly, you can find out the other associated properties by simple calculus, by differentiating single difference and double partial derivatives. So that's we can do. Mu and sigma are mean and standard deviation respectively of the infinite population of X. Okay. So how the normal PDF and CDF, that is the way we are representing the upper curve is the density curve, another second one is the distribution curve. Simple way you can represent for mu 2 and sigma 2.5, and I just hide this so that you could see it. So probability of X taking values between A and B would be represented by FB minus FA. Obviously, it could be also represented by integral between A to B. And the upper curve, which will represent your so-called density curve, that is for different ordinate values of X from 0 to minus 44, minus 66, minus 88, 10, minus 10, 10. And the function is represented like this. Similarly, you can have the corresponding distribution curve, which goes from from 0 to positive 1. This is one example. That's how your distribution and density functions are related in a similar manner. Sometimes in many of the problems, you could find that your density function for a corresponding random variable is given for a problem, and in some cases you will find that the distribution function is given for a problem. So you have to be very careful what you are reading at that time in a problem. Any questions? Okay, so normal distribution curve with mu is equal to 0. Sometimes we try to see what if the mean is 0. The cos derive the function that defines the curve as fx 1 by sigma root 2 pi exponential minus x square by 2 sigma square. And the area under the normal distribution curve provides the probability of simultaneous occurrence of errors. The moment you consider the mu as 0, the curve which will ultimately come after inserting mu as 0 will represent the occurrence or behavior of occurrence of the errors. So in the right hand side, you would see that the curve is represented by minus infinity to t. That means probability under the curve that represents the fx, capital Fx, which will ultimately represent the distribution function, and minus infinity to t, you will have this 1 by sigma root 2 pi exponential minus x square by 2 sigma square. But what is the reason for going with mu as 0 is to see how the errors would behave. Why? Because ultimately your errors would be represented in terms of plus minus sigma with respect to the mean. Okay, so that is the one way of trying to see how the errors would behave or how the errors would be given if we have such case where mean is 0. So whether mean is 0 or not, again the same figure will appear, one with the bell-shaped curve, another with the linearly increasing, non-decreasing curve. Okay, so this is a special case for area under the normal distribution curve provides the probability of simultaneous occurrence of the errors. Please remember, in the previous case, you were considering all observation at the same time. So in this case, this is the previous case, the previous slide. In this case, observation with error. In this, only errors. That is the difference. So probability of an event with the help of your bell-shaped curve, the probability of a single discrete event occurring at X can be obtained by defining an infinitely small region under the event and compute the area of the region. Okay, so px is nothing but y dx, and y is nothing but your whole function, and that is dx. So what we are trying to identify, we are trying to identify the event, discrete event. Or what is event in this case? In our case, the errors. Please remember here, in this elementary probability concept, the event is obviously related with the occurrence of error, occurrence of a random error. Please remember in this basic concept which we are discussing right from the very beginning, our main focus is towards random error. So our events are also inclined towards happening of a random error, and that is what is represented by the probability of a single discrete event occurring at x can be obtained by defining a very small size of interval. Okay, and that you can see from what properties that we can derive from calculus. We know that if we have to go from deu by dx, that means exponential u, obviously it would be eu du by dx, where u is x minus x square by 2 sigma square. So the first derivative will give minus y x by sigma square, and the second one would give y x minus x by sigma square dy by dx is minus y by sigma. So it's very simple, very small, basic calculus. Obviously, the first derivative can be put in the second one, and you will get the second derivative as this one, y by sigma square, where y is your whole function, which is represented earlier. This is simply taking the first derivative and second derivative of your function, which is nothing but this, because this is easy to understand with. This is the one which is we are derivating here. By first derivative, that will represent the slope of the line at any point. So dy by dx is equal to 0 when either x would be 0 or at y would be 0. You could see here. And so the curve is asymptomatic to x, where y is equal to 0, and peaks at x is equal to, which is quite relevant, and you could see it from the figure itself. The second derivative properties, which shows the rate of change of slope at a point, and obviously the point of inflection can be found by setting second derivative 0, and occurs when y is equal to 0, which never happens. So you could see from the figure, the point of the inflection point is represented at minus sigma. So when x is positive or negative sigma, you will find the point of inflection and 68% area under the curve. Now here comes the question, how to find this 68% area under the curve? Why it is 68? Why not 70? Why not 71? Or maybe any other value? That is the question which we need to find out. But again, in these slides, these last 3-4 slides, we have tried to identify the properties of the bell-shaped curve under this assumption that mu is 0. And what we wanted is, we wanted to see how the errors, the event in terms of random errors would occur, and what would be their properties. So from first derivative we arrive at something, and from second derivative we arrive at something which we call it, this is much of interest, that point of inflection would result at x at plus minus sigma. They are also known as point of inflection. Okay. Obviously, the similar one with going with your complete observation. Obviously, the left hand side of figure, this figure is obviously with the so-called mu is equal to 0. However, this figure represents the complete scenario where you have to represent the point of inflection with mu plus minus sigma. Okay. Another properties. These are all basic properties which is, I mean, for your better understanding. What is the maximum value of y that occurs when x is equal to 0? You put in the x is equal to 0, you get y at 1 by sigma root 2 pi. So the final top value, this one, would be 1 by sigma root 2 pi. So as sigma goes to 0, y becomes larger, the higher probability. Smaller sigma means more precise data and higher probability that sample mean is good estimate of the population. Now, last line is very, I mean, critical to know the nature of different samples. Many a times what is happening that, let's say a class of 1,000 people is there. Nowadays, first year batch consists of around 800 students. So if we all are, I mean, studying together in a class where the lecture hall comprises of 800 or 1,000 students, and you have to give certain estimates of mean of, let's say, their weights, their heights, and let's say whatever the percentage or J rank or whatever it is. So what it is expected that you go with the all 800 students, or you would go with the samples. So generally it is expected that you work in a sample of, let's say, 50 or 100 students, and let's say 7 to 8 groups are working, and you would go into the class and try to identify those samples. The samples should have been random. If it is not biased, then answer would eventually be true about the true scenario of the whole population. That is the same thing is written in the last line. So if your sample is representative, when I say the sample is representative, that means you are not biased. You have not taken the sample from a particular place, particular group, or only girls or only boys. Instead, it should have been the common representation. Then if it is an unbiased sample or a representative sample, and if the sigma is small, that means your data is precise, you can have a better estimation of the population or good estimate for the population mean. And that is one example. Just you could have good estimation for the population variance also. Why it is generally be discussed that we are talking about sample and population at this point, and the answer is very simple. You cannot work with all data at a time. Just think of exit polls. What they do, they go and collect, let's say constituencies of 30 lakh or 50 lakh, they go for collecting samples from only 5 lakh, and they decide based on that who would going to be win. And those whose sample is more representative, urban rural mix, age gender mix, they would get a better estimate on who's going to win that constituency. Similarly here, there would be a lot more chances that you have to work with the population, sorry, samples, not with the population. And in fact, with the sample given, you have to communicate the population estimates. It could be mean, it could be variance. A lot more cases would come. That means, let's say, for example, a factory of total station manufacturers. Now, all of you must recall what is total station. We'll go into the details of total station in laboratory course. But just remember, a manufacturer is producing 1,000 total station every month, let's say, or every year, let's say. And at one point of time, he has to check the consistency of the readings which one total station is giving. So what he needs to, should he go to every 1,000 total station? No, he would randomly pick the representative sample of total station, and then he would conduct such an experiment to get the estimate for the population that let's say if one total station is able to measure the true value or manufactured assembly line, there is a length of 100 meters. So how many of 100 total station would be going to measure those 100 meters correctly as 100 meter? Based on that, he would devise a mechanism by which he would give a statement about his whole set of bunch of population. And there would be a lot more other example also. Suppose a factory is of let's say Geo-Informatics company is having 1,000 employees, and what if a owner wants to study the ability to read the readings of the employees? So would he go and ask everyone to come and take the reading? Instead, what he do? He will take the sample every month, random sample by which he will try to see whether my all 1,000 employees would pick up the reading or read the reading properly or not. That's how the example of samples and population are generated. From a population, multiple samples can be drawn, or based on one or bunch of samples, you can communicate about the population estimate. At the same time, you need to understand that sample has to be representative, and if sample is representative, then smaller sigma represents the more precise nature of the sample or more precise nature of the data. If the two samples are given, the sigma represents the precision. The sigma, if it is less, you could see the gap between these two would be smaller. There would be a sharp peak of the data. And if sigma is large, there would be a pressing from top towards the bottom. That would be representing a wider distribution. Rather than a peak distribution, you would have a wider distribution. That is a low precise data. So this, with this, our understanding on properties of normal or bell-shaped curve is over. You know what is the inflection point. When you achieve this inflection point, what would be the highest or maximum value of your y that occurs at x is equal to 0, and what do you mean by sample representation? So the overall objective of giving understanding with this so-called the precision nature is that sometimes you will be given multiple data or multiple samples, and you will be asked which data is more precise, and at that time you would answer based on the so-called sigma value, that is the standard deviation. You would answer the question of precision of the nature. Obviously accuracy is a different thing that will come later on. We will discuss about the difference between accuracy and precision. Okay, so, and yes, please note down the assignment. Also, I will make a segment on the MS Team to upload your so-called assignment, and it is the chapter 5. You have to go through all the examples of chapter 5 up to 5.4. Okay, in chapter 5, all the example up to 5.4 section. That means you should go with up to page number 125, and in exercise part, similarly you have to attempt the exercises up to, I guess, 5.16. So, or initially you could work with let's say it would be a large one. You should work with 5.11. So 11 in terms of exercises, and up to 125 page all the examples that you have to attempt in your assignment. The reason is simple, that this will give you a little exposure to the book. The moment you open the examples, you would be exposed to the little content of the book also. And it is expected that since it is the only book which I'm going to refer in this course, initially for let's say 2-3 months, you should properly take the book as your reference and you should read it. Very easy book, very easily you could pick up the complex statements which we are discussing in the class, and you would be able to handle it very carefully later on when we try to solve much more complex problem. So it is expected that you try to attempt first by reading the book up to section 5.4 or 5.5, and then try to attempt the so-called examples. Later on you will find that it's very easy to pick up the exercises, and you will have to submit it in next week by Thursday. So this is the assignment, and I'll upload on the assignment tab also. There is a place where you can upload your scanned copy of single PDF. Okay, just by your name or registration number .pdf you can apply your you can upload your assignments. Okay, I'll see that. Any questions? If you have any question, you can ask.